Hey guys, this is a rundown of how the VLE simulation works for the Van-Laar model. So from the Canvas page, you should be able to download the MATLAB file, which is called the Van-Laar sim file. So once you have that, open that up, and it should open an app like this. So the basis of this app is to basically draw a PXY or a TXY diagram for your Van-Laar model phase equilibria binary system. So what we have here is a selection of three different ones. So obviously the PXY, TXY, and another TXY. So the two types of TXY, one is sims and one is without sims. So the sims one basically means that it uses the sims toolbox on MATLAB to back calculate the temperatures to draw the diagram, whilst the TXY diagram without the sims just means that it tries a number of different values for the temperature to get the correct temperature. And once it finds a correct temperature, it takes that value and plots it onto the graph. So let's start with the PXY. So here we have some Antoine constants for two different components that's already been input. These can be changed depending on the component you're working with. And then we have the temperature of the system or the pressure of the system. So for a PXY diagram, we know that the temperature must stay constant. So we know that the temperature of the system is 110 degrees. So now let's go ahead and press plot. As we can see, it's plotted the dew point and bubble point curves for the Van-Laar simulation for these two components, for the Van-Laar model for these two components. And what we can see here are the A and B variables of the Van-Laar model. So depending on the two different components, you can change the Van-Laar model to represent the right constants for your two components. Obviously, for experimental testing, these two values A and B can be quite useful because if you say have a model, an experimental model that you want to verify if it follows the Van-Laar or if it follows modules, what you can do is you can modify the A and B values and compare the plots to the experimental plots to see um, which model it follows. So now for the main difference in the simulation, and I guess the more difficult ones, is the TXY. So as we can see here, to calculate the pressure for a fixed temperature value is quite straightforward. So the bubble point pressure calculation, P1 sat and P2 sat at a constant temperature, these two values will be constant. So the only thing that will change is the molar fraction component of the vapor and the liquid. So for example, here we're plotting the different values between 0 and 1 for x1. And as we plot that, since P1 sat stays constant and P2 sat stays constant, the only two variables that do change are gamma 1 and gamma 2, x1 and x2. And since these can be very easily calculated, the diagram is very quickly simulated. So as we can see here. The problem of obviously, however, arises when we have the TXY diagram. So if we plot the TXY, you'll notice that once we click it and we press plot, it takes some time to return our graph. And the main reason for that is because what we're essentially telling the system is we have a 1.6 pressure for the system. And what we need you to do is find the temperature for P1 sat and P2 sat that matches a total pressure of 1.6 bar. And so it's basically back calculating the values. And on top of that, the Antoine constants, which are used, also have the Antoine constants form a part of calculating the P1 sat and P2 sat. And the way we write P1 sat is 10 to the power of A plus B over T minus C. Sorry, T plus C. As we can see right here. So if you see this code here, P sat 1 is 10 to the power of A1 minus B1 over T1 plus C1, where T1 is the temperature of the system that it needs to calculate. And so because it needs to back calculate this value, it can take quite some time. And what it does this for each x1 value that we have. So these steps for x1, we're saying that we want to only do it for 0, 0.1, 0.2, 0.3, and so on. If we change this to, for example, say we change this to 5, you'll see that the number of points on this graph will also change, and the time it takes to plot the graph is also less. But however, this obviously forms a sort of you have to find a balance between how many points you want to plot and how accurate you want your model to be, your graph model. So as you can see, the lines here are very straight and they don't represent an accurate representation of this component's TXY diagram. However, this, although it's not the best, it is still better. And obviously, as we increase this value, the time it takes will also increase. And so to avoid this need for back calculation, what we can do instead is we can plot using a different method. And this method, what this method does is, so here we've got 3,000 steps for the t's. And what it does is it takes the temperatures between the limits, depending on the two components. So say your limits are 128 and 99, for example. So it will take those two values, maximum values, and divide them into 3,000 different t-values. And what it will then do is then it will apply each of those t-values back into this PSAT1, PSAT2, and PSAT1, PSAT2 for the two components. And the reason this is quite important is because what it does is it puts that t-value in there for us, and then it finds the pressure. So for each of the t values, so it will give us 3,000 different pressures at a single point of x1. And then the next thing the program does is it takes the different p-values and compares them to the system p-value. So it will do 1.6 times, minus the p-value here for each and every 3,000 different steps. And whatever is closest to 0 would mean that that pressure matches the pressure of the system, which means that the bubble point pressure is at that temperature. And what it does that for each of the x1 steps as well. So in general, for the diagram we've divided x1 into 100 different steps. So for 100 different steps, it divides the t value for each one of them into 3,000 steps, and then calculates that value. An important other feature here, which is the deviation error. This is the difference in the temperature value from the actual temperature value. So here we've put 3,000 different steps for T. However, if we reduce this, say we put only 300 different steps, what we'll see is the deviation error that we have in here is not enough to find the correct p-value, because the t-value has to be very specific in order to make sure that the system reaches 1.6 bar g. So what we're saying is, if we allow the difference in the t-value we find compared to the actual t-value, if we allow it to be only 0.5%, then the system is unable to plot the diagram. However, if we increase the deviation percentage to say 10%, it will plot it. But however, what you will see is the temperature values it uses are not as accurate as they are before, because we're obviously allowing for a greater deviation, which means the exact temperature is a lot more difficult, is not found by the system. And so you can play around with these values and see the effects it has on the plotting of the model. Um, and so that's the ending of the difference between the two TXY diagrams and the background of how they're plotted, and obviously the different features involved in them. So now that we've moved away from these, now we can look at the Van-Laar model constants. So there's the Van-Laar model constants. Both values either have to be negative or both either have to be positive. Um, so if we look here, if we try and move this slider to a positive value, the program returns and says that both must be positive or both must be negative. So if we do that, then it will plot our diagram for us. Um, and once we do that, we can also see what type of deviation it results in from Raoult's law. So when both A and B are positive in this instance, well, over 1.13 or 1, we can see that the deviation is positive. And when both are less than 1, we can see the deviation is negative. And that concludes the basics of this program, how it works, and a following video will go into the background code that is involved in the simulation of the diagram to help get a better understanding of how the bubble point pressures and dew point pressures are calculated. And then we will also have a video explaining why this simulation is quite useful in phase equilibria. You'll also notice that at the moment there are two boxes here, x1 and y1. What this will do is this is still in the testing stage of the program, so it's not can't be used yet. What this will serve as is for a PXY diagram, if we have a if we put in a pressure of 2, for example, we will get these two values to plot the x1 value at 2 bar. So at this point, it would plot x1 would be at a value of around 0.93, and here will be 0.99. And what this will do is this will just make it easier for us to find the data points at the different parts of the graph for calculations. Thank you very much for listening, and on to the next video.